Leonid Parnovski will speak about classical spectral asymptotics, which is the modern mathematics.
Thank you very much. It's a pleasure to be here. In fact, I think it's the first time I have been in Cambridge for 10 years, but 10 years ago I was one of the organizers of also programming Newton Institute on periodic problems and related problems, and I spent 6 months here. And a little bit of thing that I will be talking about is related to periodic stuff. This work is joined with Jeff Galkowski from UCL and Roman Sterenberg from University of Alabama at Birmingham. And substantial part of results are work in progress, and they have been work in progress for quite a while. However, now I think we have written down almost all of the proofs, or maybe even all of the proofs. So again, it's 100 pages long, so it's serious text, and we are trying to make it more readable. So it probably will take us a little bit more time. Right, and I will start my talk by not with explaining the problem I want to solve, but with explaining slightly different problem, just to motivate, to give you proper motivation that questions I'm going to ask are going to be interesting. And this is the situation, the setting that probably all of you know. Oh, by the way, one more thing in disclaimer part, that some of you have heard earlier versions of my talk, and there will be, even if you have attended earlier talks, then there will be results new to you. So some of the results will be absolutely announced for the first time. So let us start from situation when M is a Riemannian manifold, smooth, compact, connected of dimension d, and we are interested in spectrum of Laplace-Beltrami operator on M, which we denote by H, and of course H has discrete spectrum, eigenvalues going to infinity. And one thing we study, people always like to study, is the counting function. So asymptotic behavior when lambda is large, going to infinity, of the number of eigenvalues below. So classical object. And another object, maybe slightly less easy to define, but still classical, is something that we call, people are often called local counting function, but for the reasons that will become apparent a little bit later, I will prefer to call it local density of states. So what is this function? It's just the kernel of spectral projection on the diagonal. So we take operator H. Spectral theorem allows us to consider any function of it, and we consider the characteristic function on interval minus infinity lambda squared. So this is also known as spectral projection. Right, so this spectral projection is an integral operator. It has a kernel, and we just take kernel of the diagonal at point xx. So this is a function that depends, of course, on operator, on lambda, and on point x on the manifold. And in our setting, so if ij's are eigenfunctions of h corresponding to lambda j, then of course this local counting function is sum of squares of eigenfunctions. And so as a result, the counting function of eigenvalues and of lambda is just integral over the manifold of the local density of states. So even though asymptotics of local density of states, at each point then we know asymptotics about asymptotics of n of lambda.
Eigenvalues is lambda or lambda squared?
Lambda squared. So eigenvalues are lambda squared, for which I probably should apologize, because this is what one of the co-authors insisted we should have as a notation. So this goes against my my religion, but we still have to assume
to coexist.
Yeah, indeed. Okay, so what is known about asymptotic behavior of both counting function and local density of states? So there is, there has been extensive work for something like 50 years, and more or less ultimate result is this. So we have asymptotic of the counting function. So we have the wild term lambda to power d with some constant n remainder. and remainder is all capital of lambda to power d minus 1. And if we don't have too many periodic geodesics, periodic trajectories of geodesic flow, then we can improve it to O small. So if the measure of periodic trajectories is 0, then O capital would be replaced by O small. And this is roughly speaking if and only if. So if the measure is periodic trajectories is positive, then usually we don't have O small. And similar result holds with asymptotics behavior of the local density of states. Again, we have a first term that is lambda to the d with slightly different coefficient, and the remainder is again all capital of lambda to power d minus 1. But then our enemies are not periodic trajectories, our enemies are loops. So looping trajectories which are geodesic that start at x and end at x, but they do not have to end with the same direction. So, I mean, if they visit x once, then later they could do whatever they want, we still consider them as enemies. And if there are not too many of them, then we have improvement, O capital can be replaced by O small. So both these results have been obtained using the wave equation method that was developed in the first instance by Levitan, who was my supervisor, and then of course it was developed further by other people. Yes?
When you say the measure of this trajectory is 0, you mean the union, or there are no trajectories?
So I mean, if you consider all directions starting from x that correspond, all directions that correspond to trajectories that eventually will end up in x, so measure of such directions is 0.
So average over x in direction.
But here x is fixed.
So it's in
The first thing.
The first thing is both x and direction. Second thing is just direction.
So it's the measure in the unit cotangent model?
Yeah. Yes. Exactly. Yeah.
Okay.
Yeah. Right. So okay. So and there are also results that say that basically the fewer we have periodic trajectories or looping trajectories, the better the remainder we can get. So basically, there is somehow, okay, it's not rigorous dictionary, but the rule of thumb is that periodic trajectories or looping trajectories are our enemies if we want to have good remainder estimate. Right, so another thing, I will not write down formula here, but probably people here know that if we take Laplace transform of either counting function or the local density of states, then when t goes to 0, there is complete asymptotic expansion in powers of t. And so there is sort of naive conjecture that we could make that if there are no periodic trajectories on our manifold, then we have complete asymptotic expansion of both counting function and the local density of states. Okay, I mean, of course, we cannot have complete asymptotic expansion of counting function because it's integer valued, but it's very naive conjecture, so I am allowed to make naive conjectures. And the key word here is no periodic geodesics and no geodesic loops. So the thing is, of course, that if we have compact manifold M, then, I mean, we always have either, well, we always have loop, we always have periodic trajectories, so, I mean, compact manifolds without periodic trajectories is not a great thing to study. But why do we have to make it compact? Why are we assuming that it is compact? So let's make it non-compact. So for example, let's take M equal to RD. And of course, RD doesn't have an interesting geometry, but believe me, the story will be very difficult even in the setting of M just Euclidean space. Right, okay, so Laplacian, of course, is not very interesting operator, so let's make it slightly more exciting. So let us add some first order terms and zeros order terms. Right, so V1 is, okay, it's often called magnetic potential. It's vector valued function that contains coefficients of first order. V0 is often called electric potential. It's zeros order term, and by bold case V, we denote a pair of such potentials. Right? So, okay, let's look at this operator. What can we say about its spectrum? So, if potentials go to infinity when x goes to infinity, then, okay, good news is spectrum is discrete, so we still can study counting function. Bad news is conjecture is wrong. So take harmonic oscillator, it's obvious counterexample. I mean, for many reasons, harmonic oscillator doesn't satisfy this conjecture. Right, so take our pair of potentials to be bounded. And then, Selim, are you, sorry, is there a question you want to ask?
Conjecture is what the asymptotic expansion.
Full as a complete asymptotic expansion, yes. So this is my conjecture. I will formulate it rigorously in next slide. Yes?
But something has to replace the geodesics.
What's the assumption on geodesics?
The manifold is Euclidean space. So all geodesics are straight lines.
Why do you consider geodesics for this Hamiltonian?
Okay, very good question, which I will. So at the moment, I just want to consider, because the thing is that even if we consider operator, Schrödinger operator, the results on compact manifolds would still be that, I mean, you have to take into account geodesics generated by the matrix. So from this point of view, our geodesics are straight lines. But as you correctly mentioned, I mean, proper geodesics will be slightly different, the geodesics that they will be playing a role here. Right, so if V is bounded, yes?
Can I ask a question?
Yeah, sure.
In the non-compact case,
Yes.
you have the full asymptotic expansion.
Yes, full.
And yesterday Maxime gave us this talk, and I think he may have mentioned something like for hyperbolic surfaces, in the best case scenario, we hope that there's nothing but the main term.
Okay, we are not in hyperbolic space. Yeah, I'm sorry, I was not at Maxime's talk, but
on compact manifolds.
this is non-compact, so yeah.
I understand, but still, why don't you have those extra terms in the compact case, even when things go well?
Well, morally, you have compact terms, you have these terms, but you will have them when you integrate in gamma, for example, your counting function. But I mean, it will be sort of behaving like this asymptotics, but with some oscillating terms that will sort of be no longer oscillating once you integrate many times. Right, more questions? Okay, so if V is bounded, then the spectrum is no longer discrete in general. And it's unclear what exactly we study. I mean, so okay, if pair of potential is very structured at infinity, like it is periodic or compactly supported, then we can find some natural replacements of the counting function, but in general, there is no such thing as n of lambda in this case. However, if we look at the local density of states, then it exists no matter what the potential. So this is why we prefer to study this local state density. It makes sense for all types of potentials, bounded potentials. Okay, so now let us formulate proper conjecture. So first of all, we study pairs of potential. They belong to a class that we call between ourselves USB. So USB stands for uniformly smoothly bounded. And it contains a function that are bounded and all derivatives are bounded. And actually, it turns out that this is really the proper class to study this problem, because it's, I mean, if you either increase it or decrease it, then it will be less interesting. And the conjecture which we have formulated with Roman Sternberg almost 10 years ago is that if we have any USB pair, then there are AJs which depend on x, so they are functions of x, such that we have asymptotic expansion with remainder, whatever you expect the remainder to be.
What's the difference between this class and Schwarz class?
They don't have to decay. They are just bounded and derivatives are bounded. I mean, if they decay, it's piece of cake, believe me. I mean, this is really non-decaying, bounded but not decayed. Okay, so okay, this is conjecture. And equivalent formulation of the same conjecture is that if we have two USB pairs that are identical, they coincide in some neighborhood of x, then they are, I mean, the same, they're equal to each other modulo superpolynomially decaying remainder. Now, why this conjecture is complicated? Because basically this class of operators could have all sorts of spectral properties for large lambda, for large energy. So for example, we could have dense pure point spectrum. So take one-dimensional situation with random potential, the spectrum is dense pure point, and then you can take, for example, direct sum of such potentials. So in any dimension, your spectrum could be dense pure point. So just consisting of eigenvalues, and eigenvalues are dense. You could have spectrum, as I said, being counter everywhere. So it could have, in fact, it could have as small Hausdorff dimension as you want. Positive, but very small. Right? Of course, it could be absolutely continuous, it could be singular continuous, it could have all sorts of properties. And okay, one remark that the coefficients aj, I say that there are some functions aj, but we know what they are equal to. So basically, the result of Hickrick and Palterovich of asymptotic expansion coefficients and asymptotic expansion of in the heat trace asymptotics, and they have computed these coefficients for us. So they just depend on local properties of v at point x. So there are some polynomials in v and its derivatives in x. And okay, one remark, strictly speaking, we have formulated with Roma this conjecture, assuming that there are no first order terms, but actually the conjecture is more interesting when we throw in some first order terms, because then constructing counterexamples would be much simpler when we allow ourselves to have first order terms. Right, so before formulating what is known and what we have proved, let's introduce some notation. So first of all, we say that pi is electric if first order coefficients are zero, so there are only zero order perturbation terms, otherwise we call this pi magnetic. And then one more remark is that when we have with Roma formulated this asymptotic expansion, we did not really think much about uniformity. So what I mean, is this asymptotics uniform in X? Is it not? So we didn't care, because we really proved these asymptotics for periodic potentials, and for periodic potentials, I mean, this is uniform, so we didn't really care too much. But the uniformity actually is also a very important issue here. So, okay, some terminology. We say that a pair of potential is excellent if this is as good as you can imagine. So there is complete asymptotic expansion, and it's uniform in X. So, I mean, the difference can be estimated by lambda to the power you expect times Cn, and Cn depends only on n. It does not depend on X at all. Right, we say that pi is good if we still have complete asymptotic expansion at each point, but the coefficients depend on X, but they could be chosen uniformly on compact sets. So for each compact, we can find the coefficient that works for each point X in this compact. Okay, and if potential is good but not excellent, we call it mediocre. Right, so one way of formulating the conjecture that we have proposed 10 years ago is that if we have an electric pair that is USB, it is excellent. Right, now, we still, I mean, the sort of the least we can expect if we have asymptotics at each case, so we have asymptotics for each point. Coefficients depend on each point, on the point, but we do not know whether coefficients, whether we could choose coefficients to be uniform or compact or not. So just coefficients depend on a point. So for each x, there is a coefficient depending on this point, but that's it. So for a while, we thought that it's probably more or less automatic. We didn't even think. We thought that it's more or less automatic, that EV is acceptable, so if we have asymptotics at each point, then it should be uniform on compact sets. So surprisingly, it turned out, okay, the answer is we do not know. We do not know whether acceptable potentials are automatically good. The thing is that whenever we prove that something is acceptable, then we get some estimates to prove it. These estimates are uniform on compacts, and so therefore anything that we can prove is acceptable is good. But there is no abstract nonsense result that tells us that this should always be the case. Yes?
Do you always get that these coefficients aj of x are continuous or like?
Yeah. They are some polynomials on v and its derivatives. So v and its derivatives are continuous, so aj are derivatives.
The x as functions of x.
Sorry?
When you say that they depend on v and derivatives, that is, the dependence in x is the dependence in v of x?
Yeah, it's v of x and its derivatives. So something like a naught is v of x, a1 is something like the Laplacian of x at 0 plus some number times v at 0, so it's some explicit polynomials. Right, okay, so we do not know whether these pairs exist, but recently we have found some pair that is a good candidate. So okay, we still cannot prove that this pair is okay. We do know that it is not good, but proving acceptability is actually a tricky one. Right, but because we do not know whether such thing exists, it is acceptable but not good. There is no adjective added to it. Right, so we just
in particular, if your v have some nice properties like analyticity or stuff like that, then it's immediate, right?
No.
If
You
you
want the remainder to be.
Look, for v being periodic, this was, I will mention it in the last slide. This has been long-standing conjecture that was settled 10 years ago. So this is really not as easy as you may think it is. Okay, so what has been known so far? So in any dimension, potentials with compact support are good. So this is classical result. So Popov, Shubin, and then Weidberg extended it to slightly bigger generality. So the proof used wave equation methods. So wave equation methods that people use to prove asymptotics in compact situations. So Levitan's wave equation methods. Now, when we started to study this situation, we were surprised that actually only goodness could be proved here, not excellency. So now, Ophelie, who is sitting here, is trying to actually extend these results, also prove that compactly supported pairs are actually excellent. So another situation was when the conjecture was known, so was periodic. So for periodic pairs, it was known that they are excellent. So in one-dimensional situation, it's Shubin, and dimension 2 or higher, it was actually our joint result with Roman. And similarly, if we is quasi-periodic, so quasi-periodic means finite linear combination of complex exponentials, right? Finite is keyword here. So for quasi-periodic, we also have proved the conjecture with some, minor assumptions. It's they are not serious, but we had to add some extra assumptions.
The assumptions are on regularity assumptions?
No, it's finite linear combination of exponentials. It's as regular as you want. So basically, what
Diophantine assumptions?
It's not Diophantine. Okay, so I can tell you that basically, if you have frequencies that are linear independent, they had to be linear dependent. Sorry, they had to be linear dependent with integer coefficients. So if you have two frequencies looking in the same direction, then they have to be rational multiple one of the other. But it's not quite Diophantine. It's just okay, whatever it was. Right, and okay. So again, strictly speaking, we have proved it only for electric potentials, but proof for magnetic is effectively the same. We just okay, we thought proving it for electric was already good enough. And as I already mentioned, it was settling of long-standing conjecture in periodic operators. Okay, so the methods that we used were, it was not wave equation method. it was something that we were calling the method of gauge transform, okay, because Alex Sobolev called it in this way. And this method has been sort of well known in other areas of spectral theory, or maybe not even spectral theory, under different names. So some people actually call it reduction of operator to quantum Birkhoff normal form. So some people say in quasi-periodic operators call it KAM method, or quantum KAM if you want. And yeah, as I said, many people have used it. So basically, the story goes like this. So we have learned this method from Alex Sobolev, who realized that it is really tailor-made for dealing with periodic operators. Alex learned it from Grisha Rosenblum, who used it to study pseudo-differential operators on a circle. Grisha also learned it from somewhere else, so it's actually a long story. And you may have actually seen this method under different names somewhere in literature. So basically, this method attacks the problem from completely different angles than wave equation. So wave equation takes the operator H as it is and studies wave propagation, right? So some initial conditions of what happens with solution of wave equation, and then based on our knowledge of what happens with the solution, we get some information about spectrum of H. So method of gauge transform does so it takes the operator and it tries to simplify it by using some unitary operators. So ideally diagonalize it, or maybe if not completely diagonalize, make it as close to diagonal as we want. So if I have time, I will maybe explain at the end of my talk what is this method of gauge transform. Right, but bottom line is that it was very difficult to combine two methods because they really do different things. They are sort of more or less orthogonal to each other. And for example, if you ask the question, so if we take some periodic plus compactly supported potential, is it good? The answer is, okay, we do not know. So we could not combine two methods. And this was the situation until Jeff Galkovsky joined UCL. When was it? 5 years ago, I believe. And of course, Jeff is a brilliant mathematician, and he also is one of the world of experts on the method of wave equation method. And then we join forces and try to prove the conjecture. Right, and the first thing we managed to prove is that if dimension is 1, then everything is excellent. Every USB pair is excellent. And at that time, we thought that, bingo, we have finally combined the method of wave equation method with method of gauge transform. But now we realize that this was really more sort of ad hoc method, because basically we first used wave equation method to change the operator somewhat, and then we used method of gauge transform completely from that moment. So basically we reduce the operator to periodic, and then we use method of gauge transform to deal with this periodic operator. So now we believe we really know how to combine these two methods. And okay, one comment on the side is that when we used this method, we were very proud of and proved this 1D result. The proof was something like 60 pages long. And now using our new developed method, it could be reduced to something like 10 pages. It's really, turns out to be not that difficult. Okay, so before telling you results in higher dimensions, which is work in progress, maybe I will tell you why it is interesting, why it is nice to know that some pair is excellent or good or whatever. So, okay, if a pair is acceptable, then spectral gaps are small. They decay faster than any negative power of lambda. And if a pair is excellent, then the same we could say about gaps in essential spectrum. They should be tiny. Okay, if potential is good, and suppose that we have actual eigenfunction, so solution, honest solution of equation H equals lambda u, then this solution can be large, cannot be large on this compact set. So L infinity norm decays much faster, I mean as faster than any power of lambda times negative power of lambda times L2 norm. So basically, for high energies, the L infinity norm on any compact set is small. And if it is excellent, then the same could be said for just L infinity norm everywhere, right? So even if we have eigenfunctions, they really are very tiny, have very small L infinity norms. And in particular, well, this is roughly speaking what is going on with the picture. So if we have two eigenfunctions that for small energy, it may look like an eigenfunction, right? It decays at infinity. And if you increase energy, then it will take more and more time to start decaying. And for large energy, it will really be very difficult to distinguish between eigenfunction and the wave. So basically, this is the picture that you will see in the window lambda to power 1 million. It will behave like a wave. And it will only start decaying much later than this. Right, and more generally, if you don't have eigenfunction, but if you have approximate eigenfunction, so a quasi-mode. So very good quasi-modes will have to be delocalized. So it means that if you have a function that is that is almost an eigenfunction, so let's say it has L2 norm 1, and when we apply operate h minus lambda, then we will get something small, then L infinity norm will also be very small, and therefore the size of support will have to be quite large, right? So this is one of the properties. Okay, we'll not write specific numbers here, but this is one of the properties of excellent potential. And general, if we have excellent potential, then in some sense we should think of the spectrum as absolutely continuous on any scale of any power of lambda. So basically, if you look at the spectral picture, say, and you cannot distinguish 2 points that are lambda to power minus 1 billion apart, and in X you can only look at the window that is lambda to power 1 million, then what you will see is absolutely continuous spectrum. And this is actually what some physicists were telling. I think Maciek told that he was talking to some physicists, and they were puzzled. So they looked at some operators, the spectrum is not absolutely continuous, but they measure things, and it looks like absolutely continuous. And this is probably an explanation. Yes?
Maybe you just answered it, but you just told us that you can have excellent with discrete.
Yes, discrete. But to see that spectrum is discrete, you have to go to bigger scales than lambda to power 1 million.
I see.
Right. So if those are only the scale that you could see, then what you will see is absolutely continuous spectrum.
So in any truncation that you're doing, it would look absolutely continuous.
Yes, but in reality it will not. Yes. So if you can measure things that are exponential distance in lambda, then you probably will see.
Can you say is it dimension dependent? Can you see
if it is excellent? So if it is excellent, then no matter what the dimension is, this is what you will see.
No, but sometimes in Anderson localization and stuff like that, we have this dimension.
Okay, so for Anderson localization, for example, in 1D, it means that Lyapunov exponent decays faster than any power of lambda.
But the difference between dimension 2 and dimension 3 is where it's impossible to see the localization because of the...
Well, but even if you have localization, okay, so it's continuous situation. So you will have for dimensions, high dimensions, you will have localization on at the bottom of the spectrum. So, but in principle, even if you have localization on the top, you will not see it at these scales. Right, and okay, so now finally some results in dimension 2, work in progress. So first, okay, some more terminology. So we say that the pair is decaying if both electric and magnetic part decay and their derivatives decay as faster than 1 over x, or as 1 over x. Right, so now, results in dimension 2. And by the way, so we are concentrating on dimension 2, not because higher dimensions require some seriously new ideas, but okay, at least we don't believe that higher dimensions would require serious new ideas, but they definitely would require serious extra technical things. And given that we're already at 100 pages, we decided to stick to proving two-dimensional things. So in two-dimensional situations, we have a class of pairs that we know are good. So this class is quite large, and it's very difficult to describe explicitly. So I will need more than one slide to give sufficient actually to describe this class. So this class is the weakest sufficient conditions under which we know that a pair of potentials is good. However, we know that this class satisfies some properties that I will list you. So first of all, if you take any function from your class, you add a decaying pair, then you will get again a pair from your class. Right? So we do not know whether this is true, and we suspect this is not true, that if we take a good pair and add a decaying pair, then we will get a good pair. So this, I think, is wrong. But if we take function from this class and add a decaying pair, we will get also a pair from this class, and therefore it's good. So I said that everything in this class is good. Then, every periodic pair is in the class, every quasi-periodic pair is in the class. Every radially symmetric function is in the class. Every electric potential that itself decays as 1 over x, but without any extra assumptions on derivatives. So just function should decay as 1 over x, and okay, it's still USB, so everything here is USB. But so derivatives have to be bounded, but they do not need to decay. So it's also in the class. So all such things are actually good. Okay, so now proof is actually, so now we really think this is genuine proper way of combining wave equation and gauge transform method, and we're also using some scattering ideas, some Moore type estimates of positive commutators estimates. So we're using lots of stuff. Maybe in 5 years' time we will think that again that this proof is too naive and there is more better way of combining things. But at the moment we are quite happy with this method. Okay, so now some counterexamples. So pairs that are not good, not excellent, whatever. So first of all, okay, as we have already seen on previous slide, every radial potential is in our class, so therefore they are good. But there are radial pairs that are not excellent, so therefore they are mediocre. Right, and by the way, this is probably, I believe, most difficult result to prove. So just proving this result cost us something like 10 or 15 extra pages. But we thought it's sort of important class, so we had to deal with it. Okay, so there is such thing as unacceptable pairs, so such that there is a point at which there is no complete asymptotic expansion at one point. They have to be magnetic. We do not know how to make them with electric potentials. And okay, for those of you who are interested in periodic problems, so we have constructed an example of limit periodic magnetic pairs, such that the integrated density of state doesn't have complete asymptotic expansion. So integrated density of states, we integrate in X local density of states. Very finite. So we can construct these examples only if dimension is 3 or higher. Okay, if you don't know what's limit periodic or integrated density of states, I mean, forget it. It's not really important. So those were results that we have been describing for some time. So now genuinely new results, more recent results.
Excuse me, the integrated density of state does not blow up. I mean, you integrate over all x.
Well, we integrate, but we divide by the volume of the box. So we proper average it. Okay, so first of all, again, some terminology. We say that a pair is k-periodic, and k is number between 1 and d. Okay, it's probably what you think it is. So we have k linearly independent vectors. such that V is periodic with respect to any vectors, right? So value of V does not change if with corresponding vector to the argument. Okay, and then new result. So in two-dimensional situation, every USB 1 periodic pair is excellent. So this is, remember I told you that proving this conjecture for periodic operators was really big deal, right? And now it turns out that we don't even need full periodicity. We just need, I mean, 1 periodic is also okay for things to be excellent. So that was a bit surprising. And okay, maybe I will try to explain why this is maybe not, the result itself is not very surprising. But what we also know is that if we take 1 periodic pair and add anything decaying, then result is good. So that's another thing we know. And then it turns out that probably 1 periodic pair is as far as you can push your goodness or excellency property. Because we can find 2 1 periodic pairs such that their sum is not excellent. Right, so this means that it's probably something borderline class. And we also can find a couple of 1 periodic pairs such that product is not excellent.
Sorry, how do you define the product for magnetic?
Okay, how we define the product for magnetic? Good points. Okay, there is. Okay, good question. To which, okay, forget probably this result. Then, but okay, if you, let's put it like this: if you define the product in, let's say, coordinate-wise. Okay, I think coordinate-wise would work. Okay, yeah. So just do, okay, multiply whatever you can, and then you could construct such thing. Right. So now let me answer, somehow address the question that you have asked about what are the trajectories, so which Hamiltonian trajectories of which Hamiltonian flow we are considering. And what is relationship between behavior of these trajectories and our conjecture. So when we formulated the conjecture, we naively thought that, okay, from classical perspective, the Hamiltonian that we are considering should take into account only terms with second-order derivatives. So from this point of view, Hamiltonian is psi squared, and then trajectories, of course, are straight lines, so no periodical looping trajectories. But this Hamiltonian is, of course, a little bit too naive, right? It's not really the right flow. It doesn't take into account what's happening with potentials. So actually, more relevant flow is this. So it's generated by this Hamiltonian. So epsilon here is a small parameter, and when epsilon is 0, then of course we get our straight line flow Hamiltonian generated by psi squared. But in principle, epsilon morally is something like 1 over lambda. And the question we ask about this flow is whether this flow could have, say, periodic or looping trajectories for epsilons as small as you want. And if the flow has such, say, looping or periodic trajectories, no matter how small epsilon you choose, then this is a good indication that your pair is not good or not excellent, whatever. However, if there is sufficiently small epsilon naught such that below this epsilon naught, we never have looping or periodic trajectories, then this is a good indication that our pair is actually good to excellent. So, okay, from this moment it's a little bit on hand waving because we do not know what really true dynamical definition is. Right, so semi-formal definition is this. So we say that a pair is dynamically excellent if there is epsilon naught that depends on n capital. Oh, by the way, I forgot to mention that we only care about trajectories that are, say, periodic in time polynomial in 1 over epsilon. So we do not care about trajectories that come back, but in exponential time epsilon.
Right.
So if for any n, there exists epsilon naught, such that whenever we are smaller than epsilon naught, we cannot come back in time epsilon to power minus n. Right, and so this definition is dynamically excellent because epsilon naught is not assuming on the starting point. But if we allow epsilon naught to depend on starting point, then you can give analogous definition of acceptable or good or whatever. Right, so as I said, we do not really know what the proper definition here should be, so this is really trying to find what works, what doesn't work. So we cannot really prove any formal relationship. We cannot prove that if something is dynamically excellent, then this is excellent, let's say quantum excellent, or vice versa. But in general, if it's, say, dynamical excellent, this is a good indication that it's quantum excellent, and the other way around. So now, my claim is that if we take one periodic pair in 2D, then they are dynamically excellent. Now, why is this the case? So let me maybe draw you a picture. So suppose that this is gamma 1. So everything is periodic in vertical direction, right? So then everything that happens in this strip is repeated at further and further strips. And suppose that we have a flow of our Hamiltonian. Okay, maybe let me get back to remind you what the Hamiltonian is. So if you look at this Hamiltonian, then basically the trajectory looks like straight line, and this straight line can turn around, but it turned around very slowly. So it turned around proportionally to epsilon. So direction could change, but it changes. I mean, so the curvature is actually, if it's not zero, it's still very small. Right, and suppose that I start, let's say, going to the right, and then I carry on my trajectory. So basically, up to the fact that curvature doesn't have to be large, I mean, it has to be small, we can get more or less any trajectory what we want. We can do more or less whatever we want using proper potentials, using proper V0 and V1. Because, I mean, we just need to prescribe potential at this point to make trajectory turn around a little bit. And then one periodicity doesn't really spoil fun because, I mean, we know that potential here, for example, has to be the same as potential there, but it doesn't concern what's happening with the curve. So basically, we can do with the curve whatever we want, until we actually try to turn around and get direction that is very close to the vertical direction. And then if you think about what's going on with the curve, then basically if potential does something to the curve, for example here, so for example here we have some bump, and the trajectory hits this bump on the left. So basically the bump tries to push trajectory, change the direction a little bit to the left. But then the problem is that the same bump is repeated everywhere up and down. And so our curve will have to hit the same bump effectively many, many times. And if it's hitting this bump on the left, it pushes the curve to the left, then eventually it will start hitting this bump on the right, and it will try to push the curve to the right. So bottom line is, you cannot really change the direction from, let's say, a little bit positive angle on the right to a little bit positive angle to the left. So that's why, okay, you can maybe do it, but you cannot do it in polynomial time. So that's bottom line. So as a result, we can say that one periodic pairs are dynamically excellent. What about, okay, so this is basically the explanation of what's going on. Yes?
Doesn't it mean that for any dimension you can do k equal to p minus 1 periodic?
Exactly, yes. So this will be in slide of open problems, yes. So this is, but the intuition is we think that the same result would hold for T minus 1 periodic in dimension D, indeed. Right, so this is explanation why dynamically we are excellent. So basically we can do whatever we want, but we cannot really go through the vertical direction. However, if we now have two, okay, so that's another explanation. So basically we have many barriers. So basically any direction that forms an angle epsilon to some power, I mean this angle cannot be passed, some power or some positive power cannot be passed. However, now if we have sum of two potentials with periods gamma 1 and gamma 2, for example, then we can basically, whenever we reach, we want to go through the barrier caused by gamma 1, we just can use potential V2, because as we saw, we basically can do whatever we want given a one periodic potential, unless we actually try to do something in the direction of the period. So if we are in direction of gamma 1, then V2, I mean, it's not proportional to gamma 2, so we can change the direction. And similarly, when we get to direction close to gamma 2, we can use V1 to go through. So therefore, we can find, okay, at least it's plausible that we can construct, and indeed, in fact, we can construct two periodic potentials V1 and V2, such that their sum is not dynamical excellent. I mean, proving that it's also not quantum excellent is a different story, but I mean, we can find such a pair. Yes?
Another question, sorry. But if you have product, so suppose that you have something which is excellent in dimension D,
yeah,
and want to go to higher dimension by taking a product, like being in this d-dimensional thing, good, times something bounded in the other direction. It looks like this same heuristic would still prevent you from going back once you're
say it again. So what are we multiplying? So
you want to go. You have good in dimension D, and you want to get. You have excellent in dimension D.
Yes.
And now you take anything in higher dimension, which is a product of excellent in this dimension with something in the other dimension.
Product. Okay. Because, I mean, if we take direct sum of potentials, then direct sum of two excellent is excellent whatever. So but product, I don't know about product. I mean, maybe let's discuss after the talk, because okay. So okay, now basically questions that we think are interesting in this business. So this slide has some conjectures. So conjectures means something that we either think we know how to prove, or at least we know where to start proving them. So first of all, we think that it would be extended to higher dimensions, and as you said, that one periodic is replaced by d-1 periodic. Okay, so we have proved that sum of periodic plus decaying is good. We believe it is excellent, but this is much more difficult to prove. Okay, I said that we could construct an example of 2-1 periodic such that their sum is not excellent, but probably if we work a little bit harder, we can even make it not acceptable. But okay, this will take more efforts. Right, and now open problems. Open problems means we don't really even know where to start. So probably at least one new idea would be required to settle any of these questions. So first of all, so I told you some heuristics about relationship between dynamical excellency and quantum excellency, etc. But this is really not rigorous, so we do not know any formal statements. And in fact, we even do believe that if such relationship exists, then the Hamiltonian that we have written will again be a little bit too naive. So proper Hamiltonian if such a thing exists that is responsible for quantum properties, we'll have further terms, not just epsilon and epsilon squared, but also further power of epsilon terms. So what is this Hamiltonian? And can we even prove a statement that if something is dynamically good, then this something is quantum good, etc. Okay, so we are able of constructing an unacceptable pair that has to be magnetic. So really, first order coefficients are helping us. So can we construct an actually electric pair? Because remember, the conjecture itself was formulated for electric pairs. So we still do not know whether if we say that everything electric is excellent, then we know it's not true. But if we formulate conjecture that everything electric is acceptable, it's still an open question. Okay, so one prominent example that we have already discussed a little bit of USB potentials are random potentials. And for random potentials, we haven't got an idea what is their quantum properties. Are they quantum excellent, good, whatever? Okay, dynamically we know that dynamically they are not excellent. It's actually not difficult to prove because, I mean, effectively the idea is that for random potentials everything can happen, and basically you can construct, given a random potential, you can find somewhere far away a closed periodic projector. I mean, that's not too difficult. We also suspect, we have reasons to believe that random potentials are dynamically not good. But even this is actually quite difficult to prove. I mean, we asked a couple of people who work in random Schrödinger operators, and okay, I mean, that's probably a separate, not easy project. And okay, so maybe then okay, we'll not have really time to talk about proofs, but maybe I will mention that the way we construct counterexamples, we construct potentials for which there exists a good quasimode that is well localized. And then this would imply, following the result that I mentioned, that the pair of potential is not good or not excellent, whatever. And what would this mean? So morally, the thing is that if we have a good quasimode that is well localized, then the local state density of states will have a jump at some window, some small window of energies. It will grow up much faster than it is allowed to grow up if our potential is excellent. So roughly speaking, it means that we have too much spectrum in this spectral window. So whichever examples, the counterexamples that we construct are counterexamples because we have too much spectrum. But in principle, you could try to construct counterexamples which are counterexamples because you have too little spectrum in some window. For example, a window could just have no spectrum at all. Right? And we do not know whether such examples exist. And we do not even know whether it is true that if we have USB potential, then the spectral gaps have to decay faster than any power of lambda. So next question is, so do they have to decay faster than any power of lambda? Or is there such thing as USB potential such that gaps are actually decaying, are actually somewhat large, so they are not. They probably will have to decay somewhat, but I mean, how fast they have to decay? Right. So I will not have time, obviously, to tell you about proofs, but maybe I should mention that I mean this seems to be new and, for us at least, exciting subject, fast developing now. And there are many open questions here, and we need as many hands on deck as possible. So if you or you know somebody who might be interested in this type of questions, then please, I mean, also, I mean, contact Jeff or me, or there are some younger people from our group who are currently here in the audience, so they sit around normally. So you can also talk to them, and any help would be appreciated. Thank you.
Any questions?
Yeah. What about quasicrystals? So you mentioned quasi-periodic, but what if you have infinite sum?
Infinite sum, so, okay, so almost periodic. Almost periodic.
No, I want quasi-crystal because almost periodic doesn't necessarily gives you control on the physical side as well.
So quasi-crystal, you mean something like take Penrose lattice and then take a bump at each...
and take a bump and translate it according to that, or something.
I haven't got an idea. I mean, you are more than welcome to discuss. It would be a very natural, interesting question. We don't know what are the properties of such things.
If you need to guess, you would guess that it would be like periodic, like excellent, for almost any...
Probably if you have to force a guess out of me, it's would be that it is excellent, but I mean, reality is I don't know.
So I just wanted to comment on the connection between the classical excellence and the spectral excellence. So in the weak coupling limit for random potentials, there are two famous works. The classical one is by Kessler and Papanikolaou, where they prove that classically you converge in this weak coupling limit to a diffusion process.
You are talking random now? Or
random.
Random, okay.
Random.
Yeah. Mm-hmm.
And in the sort of quantum setting, Yau and Erdős proved that you converge, so the quantum dynamics converges to a linear Boltzmann equation. So the two limits are completely different.
Mm-hmm.
And I think that might indicate that maybe also in setting, the connection might not be so
natural,
imminent.
so obvious. Okay.
And so my question is, in the random setting at least, is there something you can use in terms of, say, the Erdős-Yau work? Because this is really sort of, the wave dynamics on very long time scales of order 1 over epsilon if you're converging this epsilon. To maybe say something about the density, the local density, asymptotics?
Okay, so to be honest, we did not look too much. So what we did, we have asked some random people whether they could help. The answer was no. But I mean, maybe let's. I mean, if
it's
you...
a very different limit from the Anderson localization limit.
Well, yeah. So if you could either send the references or maybe let's have a chat. Yeah, thank you. That's. I mean, we would be very keen to start working also in this direction.
Anyone else?
The last question, can you have conditions for exponential decay instead of polynomial? What is it?
Well, I mean, so for general USB things, we don't even know that whether there is polynomial decay, right? So to have exponential decay, I suspect that if you have, say, quasi-periodic, then the decay will be extra. But okay, for quasi-periodic, we sort of more or less even know a priori that there are no gaps for large energy. But of course, it's not easy result. Okay, I don't know. I mean, there is sort of natural way of I mean, there should be some reformulation of, so on dynamical way of what happens with trajectories in exponential time, and on quantum level, whether you can improve the remainder even to something exponential. But I mean, we haven't started it yet, but it's also a natural question.
Yes, go ahead.
You had an example of a potential which is not acceptable, right?
Of magnetic potential, yes.
Right. So
yeah.
that's a failure of asymptotics at the single point. Would that failure persist if you averaged in the neighborhood of the point?
It's a good question. The answer is we do not know. I mean, this is probably the only result that I have mentioned, the proof of which is not written down properly. I mean, we think we know the proof, but it's not written down. So it's a good question, and maybe I will tell you that effectively the example that I mentioned that we think of a pair that is acceptable but not good is some sort of variation on this. So basically we take an example of not acceptable, perturb it a little bit, and then the problems somehow spread around. But this is probably relative to a question. So maybe if you ask this question in 6 months, we will have more to report.
Question about the method you didn't say much. You mentioned normal forms and KM. But the two are quite a bit different.
Yeah, I have prepared some.
Okay,
but it's
when one speaks of quantum normal forms, in general, you can stop at some order of perturbation. You don't have to go to sum the series.
Exactly. So we don't need to make infinitely many steps.
Yes.
So because for each n, I mean n is how many terms we want. We just perform number of steps that is dependent on n.
So you don't need to control small denominators.
We do need to control small denominators. So if so this slide here at the bottom. So this is small denominator. But basically we don't control them. We ignore them. We basically once we have small denominator, we do nothing for such terms.
Anyone else? Yes, go ahead.
I'm curious, can you say anything about metric perturbation?
Sorry, anything?
Can you say anything about metric perturbation?
Metric perturbation. So that is a very good question, and I mean again, this is something that we plan to look at in the future. This is, I mean, of course, also you say metric perturbation. So we can look. I mean, first step would be to look at local metric perturbation, right? Even this is non-trivial, but then, of course, I mean, if perturbation could spread to infinity, but yeah, this is also sort of very quite difficult things to do. Yeah.
So regarding your example of potentials that are not acceptable,
yeah.
Is it because you force it to loop many times around certain points?
We basically, okay, so let me again, I have prepared some slides. So the example of, so this is at the end, the example of unacceptable, non-excellent. So this is an example of non-excellent potential. So basically each of these bands, there is a bump in a band, will produce one good quasi-mode, actually excellent quasi-mode. I mean, it will be exponentially good, that is not localized. And as a result, there will be jump at some energy. So each of these circles will produce jump at some energy, and therefore for corresponding will be jump at some energy for x's that belong to corresponding angles. So for each fixed x, I mean, eventually the jumps will stop and eventually we'll have asymptotics. But the example of unacceptable, roughly speaking, would mean that all these circles will have to pass through the same point. I mean, if we just naively make the circle to pass through the same point, then at this point, of course, the potential will be infinite, and the potentials will basically we will not be able to talk about quasi-modes on one annulus because the other potentials will spoil the fun. So I mean that's one. If we want them to go through one point, we have to learn. So basically, the idea is that you can take this potential around the annulus and somehow cut it in, take one piece out of it. But this is, and make it sort of a loop without, I mean, so with nothing in between. So basically, and there will be points that all the loops will be. Okay, so this is the main problem. So basically, the example of unacceptable is a variation of this that is example of non-excellent, but this variation is quite technically non-trivial.
So I suggest we defer further discussion to the coffee break. So let's thank the speaker again.